Just a reminder to remain muted during the presentation, and then we'll have question and answer at the end. And I'd like to introduce Diane Haynes, who will introduce our session for today. Thank you.
Yeah, thank you, Julianne. And again, I'd like to welcome all of you here and all of you at home on Zoom. I assume you're at home if you're on Zoom. First, I'd like to do a little commercial about Adventures in Living. This is our 9th year of doing this program, and it seems to be one of the more popular programs, at least we think it is. I'd also like to thank Dick Martin and Debbie Dean, who are co-facilitators with me on this. We work as a good team together. Today, let me just say, if you are interested in doing an Adventures in Living, please contact either Julianne or one of us, and we will get you all set up and guide you as much as you want in doing this. I see many people in the audience here in the Oak Room who have done Adventures in Living. In fact, I see Karen Mary at home who did this several years ago. So just, don't be shy. We're always willing to work with you, and we are happy if you volunteer. Today, I have the distinct pleasure and privilege of introducing someone to you. He probably needs no introduction to many of you because he has been on the curriculum, the science curriculum committee of ILR for a number of years, and he has done many programs in the science area. In fact, if you were up at 10 o'clock yesterday morning, you probably saw him present as facilitator the Florida Museum program. And he will be doing that every Tuesday morning at 10 for the next 4 weeks. So without much further ado, I would like to introduce Dr. John Axe, and he will guide us through his very interesting life. He's not only a scientist, but I understand he's a very good golfer and a good pickleball player. Today, he's going to be telling us how to invent new menu items from the table of elements. So without further ado, here's Dr. John Axe.
So forward's the middle one there, right? Okay, is the sound okay now? Well, I want to repeat some of what Diane said. I was gently prodded into doing this, but having done it, I found that it has been worthwhile for me because it's caused me to remember and recognize many times where good timing has occurred in critical junctures of my life. So I'd like to thank Diane and Dick Martin for helping put this together. And of course, I want to thank the indispensable Julianne for everything else. Okay, let's start at the beginning. I'm an only child, born in Denver, Colorado in 1933. My parents were of comfortable but modest means. Both held full-time jobs, and in my early school years, I was wonderfully spoiled by my paternal grandmother who lived nearby with my aunt and uncle and who looked after me during the day. The duplex house with the red door is a current Google Street photo of where I lived for the first 18 years of my life, and it brings back to me a flood of memories. The now huge evergreen tree in the front yard was a seedling planted in our backyard that was transplanted after we moved away in 1951. And I remember my elementary school class of about 25 kids that had two bullies, the Montgomery twins, who on the playground tormented an unathletic, pudgy boy with thick glasses, who I later learned had by age 10 already performed piano concerts with the Denver Symphony Orchestra. His name was John Browning, who developed matinee idol looks and went on to a career that rivaled that of Van Cliburn, and who died in his prime in year 2003. He sat just behind me in an alphabetically arranged first grade class, and this was surely my nearest close approach to true greatness. I was an average student in grade school. And middle school, and then I went on to East Denver High School. East High already had a list of distinguished alumni, including band leader Paul Whiteman, the First Lady Mamie Eisenhower, and a bunch of movie stars, including silent screen star Douglas Fairbanks and Harold Lloyd. Harold Lloyd movies are still one of my favorite ones to watch. And 29 years later, Hattie McDaniel went on to become the first African-American actress to win an Oscar for her role as Mammy in Gone with the Wind. Two members of my own graduating class were also noteworthy. Jack Swigert had a pilot's license at age 18 and was the astronaut who safely flew the Apollo 13 capsule back to Earth in spite of a ruptured oxygen tank. He later won election to the U.S. Congress, but died of lymphoma before taking office at age 51. Another graduate was Marilyn Vanderburgh, the 1957 Miss America, who went on to be an award-winning author, speaker, and champion for survivors of sexual abuse. In high school, I was more interested in sports than academics. I tried them all, but the only sport in which I showed any promise at all was golf. And I was a member of the city championship East High golf team all 3 years. Someone, probably to help decide whether to attend this talk, asked me what my biggest challenge in preparing it was. I told him that it was trying to figure out how to make the table of the elements interesting. This is the chart that hangs in every classroom where chemistry is taught. Each colored square represents a chemical element arranged according to increasing number of positive charges in their nucleus, starting from the upper left and ending in the lower right. And it's arranged so that every element behaves chemically similar to the element just above it. This table was first proposed empirically by the Russian chemist Mendeleev 120 years ago, and was put on a firm theoretical basis 44 years later by Niels Bohr, who showed why electrons packed around the nucleus are required by the laws of quantum mechanics to occupy these repeating shells. The main message of our teacher, Mr. McIntosh, was how truly amazing it was that every material thing on the earth, including ourselves, was constructed out in the billions of different ways to bond together some subset of these 92 naturally occurring elements. And the chart in Mr. McIntosh's room disappeared when he gave tests, which were often based on our knowledge of this arrangement. Many of my classmates found that a class organized around the periodic tables was a boring exercise, but this was the high school class that I liked the best. And we'll come back to this in a few minutes. My high school grades were just okay, not worthy of a scholarship, but my parents agreed to pay my college tuition if I lived at home, went to nearby Denver University, and applied myself. I also joined the ROTC so as to get a small stipend and at least postpone being drafted during the Korean War. The University of Denver then, as now, was not known for its science, and the science staff had no grants to do research and just concentrated on teaching. As I worked toward a bachelor's degree in chemistry, my classes were small and populated with plenty of older, serious XGIs who served as role models for me. One smart thing I did was to figure out who the best student in my chemistry classes was and to ask if he would be interested in studying together. He came from a Christian Japanese family that was befriended by an American soldier serving in Japan after the war and who agreed to take their only son in for a U.S. education. We became friends and did well enough in our chemistry classes that a newly hired professor with a PhD from University of California, Berkeley, wrote letters of recommendation for both of us. So on graduation in 1955, we became the first University of Denver undergraduates ever to be accepted into the Cal Berkeley chemistry program. And for a time in graduate school, we shared a rental apartment. There have been a number of examples of fortunate timing in my life, as I said. Here's one of them. The National Science Foundation was established during the Truman administration in 1951, but the first real money for science scholarships came in 1955, the year that I graduated. And everyone who was accepted into the Berkeley chemistry PhD program got one of those scholarships. It covered not only tuition, but living expenses for 4 years. I entered graduate school with about $1,000 in my bank account, saved by working in summer jobs, and I left 5 years later with a nearly $10,000 nest egg. And that compares with the difficulty that putting people through school today encounter. The laboratory that I eventually worked in was located in the hills just behind the main campus, which provided a fine view of the Campanile Clock and Bell Tower and of San Francisco across the bay. My grades in high school probably would have never even gotten me into UC Berkeley as an undergraduate. And with freshman classes of hundreds of students taught mainly by teaching assistants, I probably wouldn't have done well. Looking back, I'm very thankful for the quality of the science teaching staff at the University of Denver. At Berkeley, beginning graduate students spend the first 2 years taking required courses and being interviewed by professors to sponsor and guide their research. One of the first professors I spoke with was Glenn Seaborg, who 4 years before had shared the Nobel Prize in Chemistry for his role in the discovery of 2 new chemical elements, now known as neptunium and plutonium. He said he was not now taking more graduate students because he was preparing to take over as chancellor of UC Berkeley, but suggested that I talk with a close associate of his, Burris Cunningham. Like many of the scientists at Berkeley in the mid-1950s, Seaborg and Cunningham had collaborated in the Manhattan Project, working together to understand enough of the chemistry of plutonium to make a working nuclear weapon. When I arrived at Berkeley, they were still collaborating now to understand the chemistry of the other newly discovered elements heavier than plutonium. I chose to do research under Dr. Cunningham's direction, mostly because I liked his demeanor and the teamwork that I saw within his group. Here's a picture of Dr. Cunningham seated at what is called a glove box, used to work with radioactive materials, with Seaborg looking on. One of my first training jobs as a graduate student was working in a glove box like this to recover a few milligrams of the element curium from about a kilogram of a hard-to-dissolve compound of plutonium without dissolving the plastic wastebasket container in the process. I was carefully supervised, but I wasn't comfortable working with large amounts of radioactive material. And Professor Cunningham had made clear that I would have some say in choosing my thesis project. So in my 3rd year in graduate school, with required coursework done, I proposed a thesis project. To understand it, we must again look at the periodic table. What's going on in those 2 rows of red squares at the bottom? I guess they look like purple squares at the bottom. They actually moved up into the leftmost empty boxes in the two rows immediately above, but that makes the table too wide to fit across a page. They represent 14 elements in which successive electrons fit into well-shielded inner orbits that make them all chemically similar. For reasons that we don't need to get into, they are called the 4f and 5f shell orbitals. The elements of the 4f row are called lanthanides. The actinides, as the 5f elements are called, are all radioactive, and only two, the second and the fourth, thorium and uranium, have long enough half-lives to have been found naturally on Earth in any appreciable amounts. The F shells can hold up to 14 electrons, 2 in each of the 7 orbits, which in an isolated atom all have the same energy. But when an atom combines to form compounds, those 7 orbitals are energetically split apart. And in the late 1950s, learning the magnitude of those splittings was an active field of study for the 4f electron compounds, but very little was known about the splittings of the 5f electron compounds. As a thesis project, I proposed to investigate the magnitude of those splittings on the electrons within the 5f shell of the element 91, tucked in between thorium and uranium, and shown by the lower arrow. The longest lived and the most abundant naturally occurring element isotope was protactinium-231, which has a relatively long half-life of 32,000 years and is constantly renewed as a decay product from the longer-lived uranium-235. But what set protactinium apart was in its most stable tetravalent form, it had only a single 4f electron, which would greatly simplify the interpretation of the results. Professor Cunningham agreed that this was an interesting project, and he agreed that he could get several milligrams of impure protactinium on loan from the British Atomic Energy Agency that would provide some guidance in purifying it. But it would then be up to me to find the right matrix material to perform the necessary optical and microwave experiments and to do the calculations necessary to interpret the results. The most time-consuming task turned out to be finding an appropriate compound to use as a matrix material in which to embed small amounts of that protactinium. But after a few months of unsuccessful experimentation, I prepared, and at least to my knowledge, learned to grow multi-centimeter-sized crystals of the compound that had never previously been made. It was called dicesium zirconium hexachloride. The two other parts of the project, the ones that Professor Cunningham warned he would be no help with, were more interesting. I turned for help to the physics department, and by reading and auditing classes, learned enough optical spectroscopy and theory of atomic spectra to be able to perform and interpret the experiments, and in fact, enough to pass myself off as a condensed matter physicist for the rest of my nearly 40-year scientific career. Once the samples were prepared, experiments went smoothly and the interpretation was unambiguous. It gave reliable quantitative values for the small energy changes of the 5f electrons caused by interactions of nearby atoms in a crystalline matrix. This information was later used by others to interpret results in similar experiments on other actinide compounds, and 2 other graduate students, one a physicist and the other a chemist, got PhDs using crystals that I had prepared. Having avoided the draft by enrolling in ROTC during my undergraduate years, on graduation, I was commissioned as a second lieutenant in the Army Chemical Corps. And another example of fortunate timing, by then the Korean War was over and my National Science Foundation scholarship into graduate school, I was given an additional deferment until I got my PhD. But 3 weeks after graduating from Berkeley, I was on my way to Fort McClellan, Alabama for a required tour of active duty. Fort McClellan was the headquarters of the Army Chemical Corps and was adjacent to Anniston, Alabama, which made national news when a mob of white Alabamans attempted to bomb a bus filled with student freedom riders a month before my arrival. So this was the real South. I was 5 years older than the 40 some odd other new officers in my group, and the only one with a PhD. But because I had already had a Q security clearance as a graduate student that allowed me to read classified weapons reports, after 6 weeks of mandatory basic training, I was assigned to work with two other higher ranking officers who were tasked to think about troop protection in the event of tactical use of nuclear weapons. The idea we came up with relied on a simple but pretty exact relationship, which I found in an unclassified report by a British physicist for how the diameter of the fireball resulting from the explosion of a weapon of known yield changed with time. The solutions of that particular relation could be encoded into what we called a yield card. The instructions on the back of the card specified that when the light from a nuclear explosion was seen, a trained battalion chemical officer would duck down and start counting off seconds, 1 1,000, 2 1,000, and so on. When the blast from the explosion passed him, if he were still alive, he would quickly pop up and measure with extended fingers of his hand the apparent diameter of the fireball. Connecting the appropriate time and diameter with a straight line on that yield card would give an estimate of the bomb in kilotons of TNT. The plan to test the accuracy and usefulness of these yield cards at the Nevada nuclear test site was planned for a year later. I don't know how that turned out, but today this idea could be made into an app to load onto a cell phone and would be both safer and more accurate to use. But my minimal year of active military service was over, and I was fortunate enough to have an appointment for another 1 year National Science Foundation postdoctoral appointment in the physics department of Johns Hopkins University in Baltimore. Initially, I didn't feel very welcome in Baltimore. It began the first night in the city where I parked my car on a well-lighted street in front of a hotel recommended to me by the Hopkins admission office. It was broken into, and all of the clothing that wasn't in a small suitcase that I took to my room was stolen. So I spent my first week buying new clothing and having broken car windows replaced. The Johns Hopkins Physics Department was then located in Rowland Hall on the Homewood campus. And because the department was headed by a physicist who pioneered the investigation of structure of atoms by spectroscopic methods, this was my first choice as a postdoctoral position. He had a group that had taken a lot of data on atoms containing not one, but several 4f electrons, and they were having trouble interpreting them. I thought I knew how to begin to make sense of them, but it required writing down perhaps 50 nonlinear equations and solving them over and over again while varying about 6 unknown parameters until the solutions agreed with the experimental data. It would have been impossible to do this without the help of one of about a dozen of the largest IBM computer systems in the US at that time. So for several months, my days were spent in writing Fortran code input onto punch cards to submit to a courier service that delivered them to the Applied Physics Laboratory in Silver Springs, Maryland. The next morning, I would pick up my stack of punch cards and a sheaf of printed computer output showing the differences between the computed and observed energy levels of the system under study, and then I would repeat that sequence. Today, there are program optimization schemes for this kind of a problem that can run on a laptop computer that probably would accomplish this spinning that I did over about 3 months in, I'm guessing now, probably a few hours. the laboratory that I worked in was in the sub-basement of Rowland Hall. And after several months, my desk mate, a graduate student, concerned that I was spending weekends in a windowless dungeon, introduced me to a coworker of his wife, a medical doctor's office manager named Janet Klein. On our first date, we hit it off fairly well, and soon I couldn't wait for the weekends that I could spend with this wonderful new person who had come into my life. The complication in our romance was that by that time, I was also beginning to look for what might happen career-wise when my one-year postdoctoral appointment came to an end. The Hopkins physics department dangled the possibility of a non-tenure position, but I was interested in something more permanent, one where I didn't have to balance teaching and writing funding proposals with doing research. The next instance of lucky timing for me took the form of a new reason for the rest of the physics world to become interested in the kind of research that I had just spent 5 years studying. In August of 1960, 2 months after I left Berkeley, a one-page article in the science journal Nature announced the construction of a device that made practical use of a prediction made by Albert Einstein in 1917. This diagram shows schematically the interaction of a particle of light, called a photon, with an electron in an atom. The atom can absorb the light and move the electron into an unoccupied upper level. Once in the upper level, the electron can emit a photon and drop back into the now unoccupied lower level. That's a process called spontaneous emission. But Einstein pointed out that another photon incident on an atom with an electron in the upper level and an empty lower level could cause two photons to be emitted at the same time and in the same direction. This process is called stimulated emission. Today, these devices are, of course, known as lasers, and the first example of a laser that worked for visible light used the energy levels of a small amount of chromium added into an artificial sapphire crystal to give it its characteristic ruby color. So laboratories around the world immediately began searching for other doped crystalline systems that might work better or produce different colored light. And the group where I was working at Johns Hopkins had investigated many such potential systems. And I had already spent a few years learning how to calculate the probability of light absorption and emission in these kinds of systems. So after sending out resumes to various laboratories around the country and having job interviews, I had several job offers. One was from Bell Laboratories, which had jumped hard into laser research. And I thought about accepting it, but finally chose a newly formed IBM research laboratory in Westchester County, about 40 miles north of New York City. Having made that choice, I screwed up enough courage to propose marriage to Janet. And in spite of the fact that she would have to move away from family and friends, she agreed. So on April 27th, 1963, we were married and set up housekeeping in a rented cottage on an estate in nearby Mount Kisco, New York. The first project I worked on at IBM was studying the intensity and line width of the light emitted from gallium arsenide photodiode lasers. Those are the tiny semiconductor chips that today read the information on swiped credit cards and on items purchased at the supermarket. But once these tests became more routine, I was encouraged by the lab director to think about another practical IBM concern, data storage. The so-called hard disks, which today hold the data in the IBM cloud, is essentially a high-speed version of a tape recorder, which records and reads a fluctuating electrical signal generated by a moving tape when it has regions of up or down magnetic fields impressed in it. Many materials will develop an induced magnetic moment when placed in a magnetic field, but only a small number of them will retain this magnetism when taken out of the field. These permanent materials are also called ferromagnets because iron is the best known and often used such material. Ferromagnets are one example of what I will now call patterned crystalline structures. In a piece of metallic iron, every atom behaves like a tiny magnet, which can be aligned by an externally applied field to point either in the up or down direction, which can become the zeros and ones on a magnetic tape. But there are also many materials called antiferromagnets in which the direction of the tiny magnets of the adjacent atoms point in opposite directions and therefore have no net magnetic field. And if, for example, the direction of the alignment of the antiferromagnet could be switched from, say, horizontal to vertical, this could also be the basis for another kind of binary state computer storage system. And these are just 2D examples. Add a third dimension, and as you can imagine, the possible patterns become enormous. And IBM management encouraged me to explore other examples of these kind of patterned structures. I began by using visible and infrared light as probes, but IBM offered their scientists the option of taking a 7th-year sabbatical leave of absence to work at other facilities. I chose to spend my sabbatical year at Brookhaven National Laboratory on Long Island, learning to use a new tool which is uniquely good at unraveling much more complex magnetic patterns than the simple ones that are shown here. Moving to Long Island was convenient for Janet, too, because at that time she was going back to college at Pratt Institute to get a degree in printmaking, and that gave her a shorter commute than from Westchester County. The technique that newly interested me was called neutron scattering, and it required special instruments built around a nuclear reactor. The upper photo shows the containment building of what was called the high flux beam reactor. The middle one is of the instrument floor as the instruments were being installed. The reactor core is hidden behind thick iron shielding with the instruments pressed up against their flat faces. And a small fraction of the neutrons generated in the core comes out in well-collimated 2-inch high beams. The lower photo shows the crowded space around the additional fairly massively shielded instruments needed to focus those beams of neutrons onto the materials under study and to collect and record the scattered neutrons. Computerized control stations take up much of the remaining space. And the data collection rates are low, so a day's worth of data scans are set up in the morning, and the previous night's results were studied to decide what scans to do the next day. I had fully intended to return to IBM in a year, but before the year was up, I was offered a tenured staff position at Brookhaven, and I was to stay there for 28 more years. Worldwide, there were only 3 or 4 facilities capable of doing this sort of instruments that were carried out there. So while a handful of staff scientists like myself got plenty of beam time for their own experiments, we also built up groups of outside users whom we advised and assisted in doing experiments that scientific review boards deemed were worthy of beam time. At IBM, I had also begun to think about finding other than magnetic kind of materials that might be used as memory devices. For example, ones where the little arrows represent electric dipoles rather than magnetic ones. They are called ferroelectric or anti-ferroelectric materials, which is a confusing misnomer because most of them don't contain iron, but many do belong to a class of crystal structure called perovskites, in which 6 usually negative charged atoms form an 8-sided octagonal cage around a central positively charged ion. And that octagonal cage is in turn surrounded by a square cage of 8 other positive ions. It's a very elegantly constructed structure, and one that nature often uses. And as with ferromagnets, the ordered polar effect often vanishes when the temperature is raised. And there were theoretical models that explained that specific modes of vibration within the crystal can grow in amplitude as the temperature rises and cause the ferroelectricity to disappear. Neutron scattering was also the perfect tool to study such vibrational modes. Using neutrons, we discovered and studied many other materials that spontaneously develop other sorts of subtle patterned structures. And many of them were also related to the perovskite structure and involved collective tilting of the octahedral cages. And we developed our own models that explained why, as with the case of ferroelectrics, certain modes of vibration were responsible for causing these instabilities. Over the 28-year period at Brookhaven, my name appeared on more than 150 published papers, but only on about 30 of them was I the first author. So a part of my work was as a facilitator, and I was fortunate to have a chance to work with lots of talented and, as time went on, younger scientists. And I was privileged to serve on several science committees of the American Physical Society and the National Academy of Science, and I received a few awards. The one I'm most proud of was the Warren Award of the American Crystallographic Society, recognizing important contributions to physics using neutron diffraction techniques. And as time passed, I was promoted to jobs with fancier, more senior titles associated with them. And of course, these appointments left me with less time for doing my own research. But by the early 1990s, trouble was brewing at Brookhaven. A coalition of national and regional anti-nuclear groups had just won a major victory, the closing down of the Shoreham nuclear power plant. The plant, only 5 miles from our laboratory, was planned in 1965 and was to be the first commercial nuclear power plant on Long Island. And initially it had little opposition. Construction was completed 19 years later. But in the intervening time, a contained core meltdown accident had occurred at 3 Mile Island in 1979, and 15,000 protesters gathered at the Shoreham plant in the largest demonstration in Long Island history. The Shoreham plant was ultimately dismantled, and most of the $6 billion cost was passed on to the Long Island residents in the form of increased electricity bills. To further appease the environmentalists, in its place, 2 100-foot wind turbines were erected, which produced less than 1/10,000th of the electrical energy the nuclear power plant would have produced. But it was the Chernobyl power plant disaster in 1986 that provided the final nail in the coffin of reactor-based research on Long Island. Bowing to public pressure in September 1997, New York Senator D'Amato introduced a bill that mandated the closure of the high-flux beam reactor. That date corresponded to the month that I turned 65. And though I had tenure at Brookhaven and could have stayed longer doing related studies using X-rays, I decided to retire after 29 years and pursue other interests. But before going on to my post-Brookhaven phase, I want to show some practical uses that some of the materials related to the ones that we have studied have since been refined to address. Today, you can buy a 1,000 gigabyte SUB thumb drive for about $20. That has required designing and cheaply fabricating what is called a non-volatile ferroelectric random access memory, NVRAM chip. Each chip contains 8 trillion tiny individually addressable capacitors. that even when unplugged can amazingly hold their charge for several years. And each of these elements has transistor gates that can be individually programmed to open or close in 1,000,000 times in 1 second. A schematic close-up of one of those capacitors is shown here. To achieve the density of packing, the top and bottom electrodes must be separated by a ferroelectric material, which is shown here in red, that has this perovskite structure very similar to the ones shown on the last slide. A close-up molecular cross-section of a portion of each tiny capacitor is shown schematically here. The green interior must be an excellent electrical insulator in order to maintain the voltage differences between the top and the bottom conducting electrodes that are shown in, I say pink, maybe violet, I don't know. And the size and the tilt in the conducting and insulating octahedra must fit exactly. Being able to tailor and fabricate such precise tiny devices so cheaply takes a tremendous amount of ingenuity and effort that I know absolutely nothing about. Conventional silicon solar cells convert about 29% of the sunlight energy into electrical energy. Another approach uses evaporated films of various perovskite materials tailored to capture the high energy blue end of the spectrum, which is missed by silicon. The figure shows their efficiency is growing, but still with a ways to go. However, I recently read that a British firm now advertises that a combination of a silicon solar cell with an added perovskite overlayer has a theoretical efficiency of 43%. And they have recently secured $100 million for funding for a production plant to commercialize them. I realize that I've been very sketchy in describing the details of what I actually did scientifically, because it's pretty technical, having to do with analyzing the competition between the interaction of long and short range interaction forces in crystalline materials. But before moving on, I want to suggest one analogy that might summarize, hopefully, the flavor of what I and other collaborators were up to. We were a bit like prospectors who discover an unusual rock, grind it into a pigment, apply it to a canvas, and maybe discover something like subtle changes in the color when illuminated by some light rather than artificial lighting. We think that's interesting. And we investigate and try to explain what causes those subtle changes. But make no mistake, it's the actual device makers who use these pigments that create the useful masterpieces that are the true artists here. Of course, it also takes a big investment of money to create these tiny, useful devices. In my last few years at Brookhaven, I had begun to play golf again. And when we left Long Island, we moved to a golf community in Citrus County, Florida. But I had also become interested in the physics of golf. So let me tell you a bit about that. The game of golf, dating back to the late 16th century, was first played with feather-stuffed leather balls. And the clubs were wooden hickory shafts to which either cast iron or persimmon wooden heads were attached. But when I began playing golf in the mid-1950s, the wooden shafts had been replaced by hollow steel ones. And when I took up golf again 40 years later, club makers had also begun to replace persimmon heads with hollow stainless steel ones, creating clubs that are strangely called metal woods. But along with other golf governing bodies, the United States Golf Association was concerned because their rules stated that the material and construction of the club face shall not have the effect and impact of a spring. Well, pretty clearly, a thin metal club face will deform to some extent on impact with the ball. And the U.S. Golf Association was testing such clubs to see how much they flex. I developed a simple mathematical model of impact, treating the club face as a trampoline, and did some rough calculations and sent a copy of my results to the director of equipment testing at the U.S. Golf Association, and got back a letter suggesting that I submit this paper to an upcoming golf science conference to be held in St. Andrews, Scotland. Along with a letter from him stating that the model predictions were in reasonable agreement with his ongoing measurements. This paper was accepted, and in the summer of 1998, I changed my vacation plans for that fall, jumping at the chance to visit the birthplace of golf and to play some golf at the famed Old Course, which you saw if you watched television in the last week. You saw a lot of that famed Old Course. My talk at the Golf Science Conference was well received by some of the audience and ultimately led to an offer to consult for the Spalding Sporting Goods, whose plant in Chicopee, Massachusetts, when operating at full capacity, turns out over 1 million golf balls a day. Just enough to replace the 300 million golf balls lost each year in the U.S. at that time. Here's a photo of the end of one of those 3 production lines. The first American-made golf ball was produced by Spalding in 1895, but those rubber band-wound balls vanished after the 1996 advent of another Spalding innovation, the modern multi-piece balls with a solid rubber core wrapped in a firmer rubber mantle and a dimpled urethane plastic cover. I spent the next 7 years as a consultant there. I suggested and oversaw experiments that measured the forces that occur between the club face and the ball during the 1/2 millisecond that they're in contact, and developed mathematical models to analyze and explain the results. Another project I introduced was analyzing the vibrational frequencies in the sound of the ball club impact. That information is useful in predicting how to optimize the thickness and stiffness of the ball materials in order to minimize the amount of energy left in vibration of the ball and put into the higher ball velocity instead. We also dreamed about what we called buffer balls. By developing and using elastomer materials, which were very lively when hit with impacts that amateur golfers' swings could produce, but dropped dramatically for impacts that professional golfers generate. Spalding Sporting Goods was sold to a competitor, Callaway Golf, in 2003, and they brought in their own advisory staff. However, the Chicopee plant still makes the Callaway brand golf balls. And perhaps they're still working on some of the ideas that we were thinking about 20 years ago. My road not traveled when choosing a career path was astronomy. So on retirement, I bought a good introductory college astronomy textbook, spent 6 months reading it and working out the problem sets. And then I asked myself, did I really understand that material? The way to tell is to explain what you think you've learned to others. I made an appointment with the chair of the Natural Sciences Department at Santa Fe College and asked if there was any interest in my giving a lecture or two a year at the new planetarium, which is about to open there. It's a lovely planetarium. If you haven't been there, you should go. He upped the ante and asked if I would be interested in teaching a 1-semester astronomy course. That would mean trekking up to Gainesville from Citrus County, but after talking with some of the rest of the science staff at Santa Fe College, I said, okay, let's give it a try. After 2 years of commuting from Citrus County to Santa Fe College twice a week, I changed institutions and introduced an astronomy course into the curriculum of the College of Central Florida, which had a branch campus 10 minutes from my house. And I taught astronomy there for 2 more years. Incidentally, it was while teaching at Santa Fe College that I learned about the ILR at Oak Hammock and talked my way into giving a guest lecture on cosmology here. Before my talk, I was shown around by Charles Sidman, and the first thing I said when I got home was, Janet, I've just found the place where we're eventually going to move. It took 4 more years for that to happen. We spent 14 happy retirement years in the golf community of Black Diamond Ranch, but in 2012, we moved to Oak Hammock. And while here, I've served on both the ILR governing board and the curriculum committee and facilitated a bunch of ILR programs and given a few myself. And Janet has spent 8 years helping to edit the Oak Leaf, and we both agree that this is the place we want to spend the rest of our days. And so I want to end by thanking Janet for putting up with me in our own joint 59-year adventure in living. She's made it all very special. And thank you for listening today.
Questions? Oops.
John, you can walk into the wooden floor.
Yeah, okay.
Thank you, John. You made a very technical talk, kind of interesting. But toward the end, when you were talking about the improvement of solar output, does that mean we're going to be out of date in a short time here with ours?
Well, hopefully, solar cells are going to continue to improve. I don't know what the lifetime of these solar cells are. I don't think we'll have to get rid of them because they wear out. But they are going to. Hopefully they're going to continue to improve. Here we go. Henrietta.
Thank you, John. That was fantastic. You know, the astronomy that you got so fascinated with, which you said you were always really interested in, must make the events of the James West Telescope particularly exciting.
James Webb.
James Webb Telescope. Yeah. And I wonder of the things of the first images that you saw, whether you were intrigued with the profile of the atmosphere, and whether or not you saw anything in that the rest of us that didn't do chemistry saw that is going to be interesting to follow up on.
Well, the published pictures, I found most of them were clearer and further out than the Hubble spacecraft photograph. But the thing that most interested me was the ability to take the spectra of the atmosphere around suns, because it's going to be important to know what the atmospheric concentration of oxygen, for example, is, if there's going to be life around that planet. That's an entirely new thing that we can now do with the James Webb.
Thank you. I have a question here on Zoom. John, this is Phyllis Saarinen coming to you from Colorado. So go ahead, Phyllis.
Good morning. We do that.
Hi, Phyllis.
Good morning. John, you've convinced me it was probably a good idea that I didn't major in chemistry in college. Especially not nuclear chemistry, but thank you so much for all the details. Very interesting talk for Drew Pierce and me. But Drew has the question, so I'll turn this over to him.
John, I thought it was a very interesting talk, and I wanted to ask you during your time teaching astronomy courses, what did you find was the most interesting thing that the students said or wanted to know or discussed with you? Can you give us some idea what the students were particularly interested in during those years that you spent teaching those courses?
Well, many of the students didn't ask questions. To get them to ask questions it was always a problem for me. But I think most of them were interested in the entire history of the universe, going back to 13 billion years, right? And how it's possible to get that kind of information.
Mhm.
Okay,
So
thank
just
you.
the broad scope of the paradigm that we have that explains how the universe developed and so on.
Mhm.
Okay,
Thank you.
thanks.
All right, back to the Oak Room here, Mr. Petway.
Yes, Richard.
What a wonderful eclectic journey you've had. I want to, after St. Andrews watching this weekend and being part Scot, Scottish is my wife and I, which has a great fondness for Scotland. I looked at your schematic of the ball hitting the surface, and I noticed the ripple of transition of the energy, not only to the face of the ball, but to the reverse side of the ball.
And then bounces back.
Yeah. And so I'm kind of interested in that extra motion because that tells me a little bit about the density inside the ball and the various
Yeah,
densities.
and the elastic stiffness of what makes up the ball. Yes.
Right. And so I'm kind of wondering, do they want, and you did say they produce balls that would be good for amateurs, but not pros, and it's probably the speed of the shaft hitting the surface. And now I noticed that golf heads on drivers and others have adjustments in the mechanism of the surface of that particular head. And I kind of wondered, do they do that research about to improve the ball characteristics? And is Titleist the biggest selling ball a Spalding ball, or is it?
No, that's the Titleist is a competitor with Spalding. Callaway balls are essentially Spalding balls. The same people that worked at Chicopee when I was there are to some extent still there. So they're different, but they all have their own trade secrets.
Yeah.
But and shaping the thickness of the face of the driver is now something that they have been working on. So there's a lot of experimentation of knowing what it is they can get away with without violating the rules of golf.
All right, back to Zoom here. Rick Gold, go ahead.
Thanks, John, for a fantastic presentation. I'm interested in your feelings about the future of nuclear energy, given the fact that Brookhaven was affected by the protests against 3 Mile Island, and that Chernobyl has really set a damper on the whole nuclear industry. Do you have insights into whether nuclear power plants have become much safer and what the future is for them to deal with climate change?
Well, it's my opinion that safe reactors can be built. France has already generating the majority of their electricity for many, many years using nuclear power. I think it's important to settle upon a fixed design and build many of those kind of fixed design power plants. In the United States, Westinghouse or GE will build have built site-specific plans that are maybe not tested as well as they ought to be. But I believe that it's going to ease the difficult transition we make to burning non-fossil fuels by using to a much more extensive degree than we do now nuclear power. And I believe it can be done safely.
Thank you. Wait.
Germany has caught in this gas problem and in essence has withdrawn from the nuclear power grid.
Right.
Or started the process. There's
Right.
a long
Well, yeah,
process.
they shut down all their nuclear.
Yeah.
reactors.
But do you think that they will restart them? Or, because it looks like there was even a statement in the paper by Russia saying it would meet all of its current obligations for gas through the near future, but there could be changes in the pipeline supply from Russia. So do you think, just an estimate, do you think that Germany will reduce and go back to nuclear power because gas is going to be problematic for them?
Well, Germany and France are have two entirely different feelings about nuclear power. I don't think Germany can just instantly start up their nuclear power plants again. But Will, you may have some thoughts on that.
Well, we have the mic in the back now.
Okay, all right. So
I have some thoughts, and I think
two wrongs don't make a right. Yeah.
And maybe we'll hear more about this in the nuclear power
Yes.
series that we have on Tuesday afternoons. Thank you. Back in the back?
for those of you who are interested, I suggest you
Can you speak right into the microphone?
consult Dr. Google and type in small modular nuclear reactors, and you'll see where the future is coming.
Yeah. I'm interested in that, and I know there are companies that are working hard to try to get those plans. Bill Gates, for example, is very interested in getting involved in that. So a lot of money's has to flow into that, but I hope that it works.
Any more questions?
Yeah, we'll. You have.
Chernobyl never should have been built. 3 Mile Island was adequately contained.
Yes.
Any more comments or questions? Okay. Oh, Richard.
I've done some research on Babcock-Wilcox designed nuclear power plant.
Oh.
And if you review that particular design, it is the same one at 3 Mile Island and Fukushima. Were both Babcock-Wilcox designed plants.
Oh, I did not know that.
Remember keeping the nuclear storage on the 3rd floor or 4th floor up was a characteristic for both of those plants. And what I found is the capital markets did notice those differences in plants by design. The companies that use the Babcock-Wilcox after 3 Mile Island and after Fukushima really took a hit. So it's not just the scientists that are paying attention to the design of these plants. It's also the stock market penalizing the companies that did.
Sure.
Any more comments or questions? Okay. I would like to take this moment to thank John so much for being here with us. And I have one more thing I need to say to John. I would like you to tell us what you did at St. Andrews in terms of setting a record that you broke.
Yes, here's an interesting fun fact. I played golf at St. Andrews 3 times. The last time I broke a record for the old course that lasted for 50 years, and I broke it. The catch is that record was set in 1859.
Thank you, John.
Yes.
Okay, thank you. And thank you all so much for being here with us today. And next week, we'll see you back here again or on Zoom. And we will have Mary Sue Koppel here with us. It's another down memory lane. So that should be a good one. Thank you.
Thank you, everyone.